let us straight away start with diode circuits today. Okay, probably you are already familiar with the operation of a PN junction diode. By diode we mean PN junction diode. Okay, so PN junction diode. Okay, the symbol is like this. It has two terminals like this. You can call the P side, that is, this arrow is on the P side, and usually that is called anode, and the other side is cathode. So this is the N side. It's a PN junction diode. So there is a P side and N side. P side means p-type semiconductor. Now we will not go into the device physics because that is already covered in your previous course, like current voltage relationship, the derivation of that relationship, drift, diffusion, all those details we will not go into. We will start using this diode in the circuit. So that is what is the focus. This course is focusing on the circuits which make use of these various kinds of devices. All right. So in order to use any device in a circuit, we should know what is its voltage current relationship. So usually you can start with what is called as IV characteristics. Voltage, if I plot on the horizontal axis, and current I plot on the vertical axis, I have what is called as the IV characteristics. So for diode, since it is a two-terminal device, you can define a voltage like this, and you can also define a current which is passing through it. Okay, so voltage is measured at the positive terminal with respect to the negative terminal. Negative means cathode terminal. The voltage at the anode terminal or the P side with respect to the N side. So that is what this V, which I plot on the x-axis, and by current I mean the current that is flowing into the P side. Okay, that's the direction that I am going to take. So positive current means current is entering in the P side and it is leaving the N side. Okay, as it is shown, the direction here. Okay, so if I plot this, the actual characteristics of a PN junction diode will look like something like this. So initially it will be 0 and then it will increase like this, and on the negative side there may be a very small current, negligible current, which will we usually depending upon whether the material with which we make the diode, it is germanium or silicon, depending upon that this current magnitude will be different. And similarly the voltage at which the positive current increases will also depend upon the material. Okay, so if you look at the characteristics, it is basically in two quadrants. One is the first quadrant. So this is the first quadrant. This is the first quadrant and this is the third quadrant. So the characteristic is either in the first quadrant or in the third quadrant, and the first quadrant correspond to what is called as the forward bias. Forward bias, because we are applying a positive voltage and the current is also positive. So that is forward bias operation. And the third quadrant is basically giving us reverse bias condition. Okay, so the diode can be either forward bias, that means you can apply a positive voltage or a negative voltage, and characteristics are very different. Suppose we are using a silicon diode, which we normally use in semiconductor based circuit, device based circuit. So we mostly prefer silicon because it has lots of advantage, which you might have come across in the previous course. The cut in voltage. Cut in voltage is defined as the voltage at which the current does enter into milliampere regime. Okay, so initially the current will be very, very small, so it is negligible. Usually this axis is plotted in milliampere. This axis is vertical axis, in especially for positive quadrant characteristics, that is forward bias characteristics, it is plotted in milliampere. So if you take milliampere scale and plot this IV characteristics as you apply voltage, in order to see any significant current, when you plot the current in milliampere scale, you need to at least apply some 0.6 volt. Okay, so when you reach 0.6 or 0.65 volt, that's when the current begin to rise, and once it goes beyond 0.6, then the current exponentially increases. Okay, so this 0.7 volt is sometime taken as 0.7 volt. Okay, so this is what is referred to as the cut-in voltage. Okay. And in the reverse bias, usually the current is plotted not in milliampere scale, but you plot in microampere scale. So this is microampere. So in microampere, you will otherwise you will not be able to see any significant current. So the reason why we plot in microampere here in reverse bias is in order to see there is a small current that is flowing, and usually that current is a constant current. Okay, it's a constant current. Okay, it quickly rises to the constant current, and that current magnitude is also a significant quantity of the diode. So this current magnitude is it also depends upon whether it is made of silicon or germanium, but if you take say silicon, it will be of the order of 1 microampere. Okay, so it's a very small current. And now this also has a name. This current, just like this voltage has a name, this current is called as reverse saturation current, or I0. Reverse saturation current. Now mathematically you can put all this characteristics in an equation which is called as the diode equation. So diode equation is a mathematical expression between current and voltage. So it is given as I is equal to I0. I0, I already told you what it is. It is reverse saturation current, and magnitude is something like 1 microampere, or sometimes it may be even lesser than that. It depends, the exact value depends upon the doping concentration and various other parameters relating to the material and the construction of the diode. So I0 into e raised to qV by kVt minus 1, where V is the voltage. So kVt is basically a quantity that is made up of kB corresponds to Boltzmann constant, which is 1.38 into 10 raised to minus 23, and T is basically the absolute temperature. So this is basically the absolute temperature. Okay, so absolute temperature, if you take say if you take it as if T is equal to, so this value for T equal to 300 degree Kelvin. Okay, so this is in degree Kelvin. So room temperature, usually we take 300 degree Kelvin. So if you take a 300 degree Kelvin, this value turns out to be 0.026 electron volt. Okay, electron volt, I hope you are familiar from the device physics. Basically you divide by Q. Okay, so there you can see that there is a Q here. Okay, so if you take that Q in the denominator, so this will be like this. Okay, so when you divide by Q, you get 0.026. Okay, this value to be 0.026. So that's basically the value of KT by Q. It is 0.026 electron volt. If you express it in milli electron volt, it will be 26 milli electron volt. Okay, so if you rewrite the diode equation, so I is equal to I0 into e raised to V is the positive voltage that you apply, divided by 0.026 minus 1. So this is basically the diode equation. So this is the equation where I have taken T is equal to 300 degree Kelvin. Okay, so now as I told you, in the characteristics there are forward bias characteristics and reverse bias, quadrant 1 and quadrant 3. So in quadrant, so this is basically called the diode equation. Let me so in quadrant 1, so if you compare in quadrant 1, so in quadrant 1 V is positive. So V is positive means you see that in the exponential here V divided by 0.026. Now when the V value, the value of V become say 10 times greater than 0.026. Okay, 10 times greater than 0.026 means 0.26. Okay, that's a typical value that you can apply. So this is quadrant 1. I am going to rewrite this expression. I is equal to I0 into e raised to V by 0.026. I can neglect this 1. Why? Because if V is greater than, so I am assuming that V is greater than say 10 times 10 times let me write it as 10 times 10 into 0.026. Okay, so if V is 10 times greater than 0.026, which is the denominator part of the exponential, the numerator is 10 times greater, then it is e raised to 10. E raised to 10 is a very huge number, and therefore we can neglect 1. So that's the philosophy. So we can approximate the forward characteristics, which is usually the case. Any interesting voltage that you apply, this V will be at least 10 times greater than 0.026, and therefore you can write it as a exponential relationship without any this minus 1. And similarly, if you approximate for quadrant 3, where you have the reverse bias condition, V is going to be negative, because I told you when we say the polarity of V, we are talking about the voltage at P side with respect to N side, and therefore it will be negative for reverse bias condition, because for reverse bias P side is applied with a negative voltage compared to the N side. If that is the case, there will be a minus sign also here, and if you have a negative minus 1 or minus 2 volt, then it will be e raised to minus 10 or something like that, because in this fraction the negative, it's a negative number, but denominator is very small, 0.026. So e raised to minus some big number, e raised to minus 10. Just like here I said e raised to plus 10, it will become e raised to minus 10, and therefore it will be 1 by e raised to 10, which is a very negligible quantity. You can neglect with respect to 1. So you only need to keep the constant term, which is going to give you minus I0. So under reverse bias situation, you have minus I0. That's why I said when you apply a negative voltage, so usually one more thing I would like to say is that the voltage that you vary here, here you vary say in points, fraction of a volt. You don't vary like 1, 2, 3, etc. When you forward bias, you can't do that, because the current is going to rise very rapidly according to this relationship, forward bias quadrant 1 relationship, and that will tremendously increase the current, and we need to limit the current to say less than 50 milliamperes, and therefore we cannot apply any voltage greater than 0.75 or a maximum maybe 0.8, not beyond that for a silicon diode. For a germanium diode it may be a different value. So cut-in voltage is something like 0.6 to 0.7. Okay, so that's the range of cut-in voltage for silicon. For germanium it is like 0.3 to 0.35 etc., which is smaller. And gallium arsenide it may be something like 2 volt, okay, 1.8 to 2 volt etc. So depending upon the material with which you make the diode, the cut-in voltage, the value of the current becomes significantly entering into the milliampere regime, or at least a fraction of milliampere, which is visible when you plot in the forward bias characteristic. So I said here we go like 1, 2, 3 milliamperes like this, and here we go in fraction of volt, 0.1, 0.2, 0.3 etc. Whereas when you plot the reverse bias characteristics, you usually go like -1, -2, -3, larger voltage, and here the current is like in microamperes. It's like 1, 2, 3 minus 1 microampere minus 2 microampere. So because I0 is of the order of microampere or even fraction of a microampere depending upon the material. For silicon it may be greater than 1 microampere. For silicon it will be lesser than 1 microampere. For germanium it will be more than 1 microampere, maybe 10 microampere or 100 microampere, something like that. So that's basically the diode characteristics. You can capture it. Now an approximation of this idea, this is the real characteristics of the diode, okay, what I have and you can derive this. Probably you might have derived it in your earlier course, I do not know, but you are supposed to know this from the earlier course, the derivation of it. Now we are going to idealize the operation of this device. When you use this diode in a circuit, we can approximate the function of the diode, leaving apart the complete accuracy. You may not require to use this exponential expression, because that would make it even we have simplified it for forward bias and reverse bias, but still carrying out with the exponential expression for the forward bias situation, it is going to lead us into difficulty for calculating the voltage and current etc. So in order to simplify this analysis of circuits, we take a simpler approach. We talk about what is called as ideal diode. Okay, so ideal diode, so it's an idealization. So what is an ideal diode? Ideal diode is defined in terms of its characteristics. So just like earlier, here now we say that it has a characteristic something like this. What does this mean? That means if you try to apply a forward bias, there will be no voltage drop across the diode, but the current can be varied without so this is ideal diode characteristics. Okay, so this is again I and this is V. So whereas if you apply a negative voltage, say -1, -2, -3, you have zero current. So I is equal to 0 here, and here V is equal to 0. Okay, so an ideal diode which has ideal characteristics like this never exists in practice, but this is the most simplest approximation one can take in order to quickly find out how the voltage in a diode circuit will look like. So you can immediately come across or you can immediately find out the voltages and currents in a circuit. Alright, so here you can see if you try to apply a positive voltage, that is forward bias the diode, it can't take any volt. It is something like a short circuit. Okay, so this means like this. So when you have forward bias, it is like a short circuit. Now short circuit means what? You can apply any current to pass through the diode, but the voltage drop will be 0. So that's the equivalent circuit of a diode. And whereas in the reverse bias situation, what will happen? Current is going to be 0, I is equal to 0, and you can apply any voltage. It's like an open circuit. So diode is like a switch. Okay, when you apply a forward bias, it closes. The equivalent is that it's like a closed switch, and when you apply a negative voltage, it's like an open switch. Okay, so this is a very simple picture, but it helps to quickly find out. So let's look at some circuit which involve diode and quickly find out what is going on. Okay, so this one of the most basic circuit or most important circuit which we use very often with which involve diodes is a rectifier. So rectifiers, rectifier circuit. Okay. This is one of the fundamental application. For this reason, even diodes are called rectifiers sometimes. Okay, so rectifier circuits, there are various kinds. So the simplest, if you look at it, is a half wave rectifier. Okay, HWR means half wave rectifier. Probably you might have studied this in +2 and diploma, so it may be a repetition. So you have a sine input, okay, which I am going to call it as say V in. It's a sine wave. So sine wave which has a polarity like this, and in half wave rectifier you use the diode along with a resistor, and the resistor is basically the load resistor. Maybe it could be a bulb or something like that, or some other load. So we can just name it as R. So this is a diode, and now we will assume that the voltage across the diode is VD, okay, in order to distinguish it from the output voltage, which we will call as V naught. Alright, so this is a simple circuit, one diode and one resistor, and you have a sine wave. The sine wave, if I draw the input here, so this is the sine wave. So with respect to time, the amplitude of the wave changes, and there is a peak voltage to which it goes, and then in the negative half cycle it will go up to minus Vp. So this is the 0 point. So this is the plot of V in, how it varies with time. Okay, so this is oscillating. There will be some frequency. So like this, and if you want an expression for this V in of t, it is basically Vp sine omega. Omega is the angular frequency, so t is given like this. This is 1t. So if you want to write it as in terms of omega, you can write omega t. Otherwise, if you want to write it in terms of omega, you can write it as 2 pi by t, and so this is the expression. So phase is 0 at t equal to 0, and so when t equal to 0, sine is 0, and so it starts from 0, and then it as time increases, the voltage increases. It reaches a peak when this omega t becomes pi by 2. So this is the expression. Now we are interested in knowing what is the output voltage V naught. So we need to plot it just below it. What is going to be the output voltage? Okay. So this is V naught. So how do we find out? So as I told you before, the characteristics of diode is what we need to keep in mind in order to find the output. So finding the output of a circuit is what we call as analyzing the circuit. We are giving some input, there are some components in the circuit, and we need to find out what is going to be the output. And so the process of finding out the output for a given circuit and for a given input, so that process is what is called as analysis of a circuit. The other thing that we do in circuits theory is designing a circuit. Okay, we have an input and we require a particular kind of output, and therefore we need to decide, we need to come up with a circuit with its values, appropriate values, so that we will get the required output. So that's called design of a circuit. So as engineers, mostly you will be engaged in doing any of this, either analyzing a circuit or designing a circuit. Okay, all right, so let's see what happens. Okay, so I'm going to take an approximation here. Approximation means I'm going to assume that Vp, that means my peak voltage. So for analysis, it's important what is the value of Vp, because if Vp is very, very small, say less than 0.5 volt, it's a small sine wave, and then you know that the diode is an open circuit. It will act like an open circuit and no current flows. But right now let's take it as an ideal diode. So if you take it as an ideal diode, then I don't need to even consider the value of a Vp. But still, let me specify explicitly that Vp is much greater than the cut-in voltage of the diode. Okay, for ideal diode, this cut-in voltage is 0 actually, as the characteristics I have drawn. But if it is a real diode, then this condition is important to be kept in mind. Otherwise, the output will be different. I'll come into that a little later. But let's now treat it as ideal diode, which has 0 voltage as the cut-in voltage. Any forward bias voltage is, even if it is a millivolt, it will make it a function like a closed switch. So during the positive half cycle, it is a closed switch. So I can redraw the circuit for positive half cycle and negative. So this is the positive half cycle, and this is the negative half cycle. So during positive half cycle, I can redraw the circuit like this. So this is assuming ideal diode. Okay, so which means that my Vd is equal to 0. So all what I have applied, that is my V in, comes as V naught. If the diode is a short circuit, acting like a short circuit, which it will do, an ideal diode will do so. When you apply a forward bias voltage, a positive voltage, I am applying a positive, we are looking at the positive cycle. So it is a short circuit, and whatever is applied at the input comes at the output, and therefore, as you know, V out is equal to V in. Okay, you will get exactly whatever you have applied, you get Vp here. Now if it is a real diode, what is going to be the difference? Some amount of drop will be there across the diode. It won't be Vd equal to 0, it will be Vd equal to the cut-in voltage, approximately 0.7 voltage, 0.7 volt for silicon diode, and therefore the peak will go not up to Vp, it will be Vp minus whatever is the cut-in voltage. Okay, so that's the difference between ideal diode and real diode. So ideal diode, it is very easy to come up with the output waveform. You just need to replace the diode with a short circuit when it is forward bias, and now, so this is the forward bias situation. Now if I redraw the circuit for a negative bias, so whenever it is a negative input voltage that I apply, okay, still I am taking the reference like this only, but the value of V in is negative. Okay, so therefore my equivalent circuit is going to be like this. So I have a resistor, I have a equivalent of diode, which is an open circuit because V in is negative. Okay, so V in is less than V in is less than 0. So here V in is greater than 0, so that's positive. Here V in is less than 0, which is negative. Therefore the diode, we need to replace it with an open circuit, and the output is equal to 0. So here V of t is equal to V in of t. Okay, so this is the negative half cycle, and the output is 0. That's it. And then whenever the positive half cycle comes, so this is reverse bias, we need to, so forward bias is applicable for positive half cycle, reverse bias is applicable for negative half cycle, and this thing repeats. So this is what is rectification operation or rectifier circuit, half wave rectifier, because only half of the cycle is coming at the output. Whenever it is positive, it will just pass through and it will come across the resistance, and whenever it is negative half cycle, nothing comes out, it is 0 voltage. Alright, so now if the diode is a real diode, okay, how will if real diode, so here I told you the output depends upon the cut-in voltage. Okay, so again let me redraw the input. So this is Vp may be like 10 volt or something like that, so this will be minus 10. So this is T, this is my V in of T, and just below that I would like to draw. So I need to know when it is forward bias, when it is going to be reverse bias. This information is required. Not only that, what is the cut-in voltage? That's an additional. So let me say that the cut-in voltage is somewhere here. Okay. I'm not specifying the actual value, but I'm just drawing a line which represents the cut-in voltage. That means it will be forward bias. So now I am taking a characteristics of the diode which is slightly different from the ideal diode characteristics. Ideal diode I have earlier drawn, but now I am going to do a better approximation, and the better approximation is something like this. So this is my voltage, and this is my current, and this is my V cut-in. Okay, V cut-in voltage, usually it is denoted as V gamma. Okay, so which is called the cut-in voltage. So let's say this is 0.7 volt. So that means the green line which I have drawn here corresponds to 0.7 volt, and Vp may be like 5 volt, 10 volt depending upon the input waveform, but we have taken an approximation that Vp is sufficiently greater than 0.7 volt. Okay, under that approximation I am drawing, otherwise this waveform will be under 0.7 if Vp is less than cut-in voltage. So V gamma is equal to 0.7 volt. Okay, so the characteristics, now this is slightly better approximation because it will take into account of the voltage drop across the diode, which is not 0 when it is forward biased, but it is 0.7. This is a better approximation, but it is also simple enough for us to find out the output waveform in a better way. So what's the difference? Now the diode will act as a, so the equivalent circuit let me draw first, and then let me come to the output. So when you forward bias the diode, the equivalent circuit is now going to be looking like this: a battery and a resistor. So diode is going to be replaced with a battery, and what is the value of this battery voltage? It's 0.7 volt. Polarity is as shown, and I have this. So this is my V in of t. I'm applying 0.7 is dropped here. So So this is valid when V in of t is greater than 0.7 volt, okay, or V gamma. So only then it is this equivalent circuit is valid, not when V in of t greater than 0. Okay, so we are talking about this part, okay, where it is going to be vertically. So it is happening at 0.7 volt. So whenever the positive voltage cross this green dotted line, only then this equivalent circuit is valid. Otherwise, whenever this condition is not satisfied, that is V in of t greater than 0.7 volt is not satisfied, the equivalent circuit is given by an open circuit. So this is slightly better approximation because it takes into account the cut-in voltage information also. So here VD, so this is VD. So whatever is VD is basically V in this case. Okay, so here we are saying V in of t is less than means it could be positive or negative. Positive means positive values less than 0.7, or it could be negative. Okay, both will satisfy V in of t less than 0.7 volt. So it will be an open circuit and nothing flows. Now, so what is going to be the difference? Now let's come back to the output. So the difference is that it is not at 0 the positive half cycle at the output starts, but it is when the input voltage is crossing okay. So it's only when the input voltage cross this so it takes some short time for the input voltage to rise above the 0.7 voltage in the positive half cycle. So this is the positive half cycle, but the entire positive half cycle doesn't come, only a portion. Okay, so the actual positive half cycle is from here to here. So this is our T by 2. The entire T by 2, it is not conducting, it is a little less than that T by 2, because only after a short time that it is going to cross above this green dotted line, and similarly it doesn't go up to 0, but whenever it get lesser than 0.75, immediately equivalent circuit become this one. So the remaining time, so more than T by 2, it is going to remain 0, and then again like this. Okay, so and this level is also important. Now it is Vp minus 0.7 volt. Okay, so it is not going up to Vp, it is little less. This is a more practical situation, because this is going to become more and more important when Vp is value is not significantly larger than the cut-in voltage. Say 1 volt if you apply, you can really see the difference practically what you get and what you get using the ideal diode approximation. That's going to be very different. Okay, because very small fraction of the positive half cycle is the diode is going to conduct, and only when it conducts you have the output voltage. So here is the output voltage. So you can write the output voltage here as V in of t minus 0.7. Okay, and here output voltage is equal to 0 because no current flows. Okay, so here there is a subtraction by this voltage. By KVL you can write this, right? Whatever is the V in minus 0.7 is the output voltage. Alright, so that's a simple or the simplest circuit one can think about with diode. So that's just one circuit. Let me also go into one more example, which is a similar circuit, but I'm going to so this is example number 2. One more circuit. Okay, so this circuit again I have a sinusoidal means sine wave input. Okay, I have V in of t just like before, but now I am going to give you some real values. Here there is a resistance 100 ohm, and then I am not putting, this is not a rectifier circuit, it's a different circuit. Okay, but so there is a diode here which has some current ID, and then there is a voltage. This is a DC voltage source, 12 volt. So this is the circuit that we need to analyze, and I should also give you what is the input voltage. Okay, so let us be specific about the input voltage. I will draw the waveform. So this is again a sine wave. Okay, and I would say that this is 24 volt. It is given, okay, in this problem that it is 27 volt. The frequency is not mentioned, so we will take it as T. Okay, so now what is the question? The question is this: find the fraction. Okay, so the question is this: find the fraction of each cycle. Find the fraction of each cycle during which the diode conducts. Find the fraction of each cycle during which the diode conducts. So that's the question. So how do you do this? Okay.
So here V of t is 24 volts.
The VP, this is VP.
VP is 24.
Right.
Okay.
Vin is a sine wave. So if you write the expression for Vin, so what I am plotting here is V. So this is Vin of t. Like before, we can write it as say 24 sine 2 pi by t. This way you can write. Okay, so this is the input voltage that you apply. Now the question is that find the fraction of each cycle during which the diode conducts. So we know that depending upon the condition that we earlier specified, there is some point of time it is going to be forward bias, and some point of time it is reverse bias. In one complete cycle, what point of time the diode is going to be forward bias. So let's assume that Vd is the voltage across diode. So we know that, so the operation of the diode, we know that so let's assume that again it is an ideal diode, because that will an ideal diode approximation is okay to be taken because Vp is quite large compared to 0.7, and therefore ideal diode approximation doesn't much differ from the actual real operation of this circuit. Okay, but if Vp is not sufficiently large, say close to 2 volt, which is comparable to 0.7 volt, so at least 10 times larger, you are safe to take this ideal diode operation, where we will assume the diode will be forward bias when Vd is 0 or above 0, and it is reverse bias and open circuit when Vd is less than 0. So we have a constant voltage on the N side. Okay, so we have a reference. This is the reference voltage. This terminal is the reference for input and output. We have a constant reference which we call as the ground point. Ground is usually taken as the reference. So input is also measured with respect to that reference point, and output is also referred with respect to that. So output is basically 12 here if you take this as the output, but that's not much interesting to find out, because that's quite evident that it is a DC voltage source, so output will always be 12 volt. Okay, so if I draw output voltage in this, it will be just half of this. So this is my output. So this is 12 volt. It doesn't change at all. Okay, so I mean this is my V of t, so that will remain at 12 volt. That's not what is asked. What is asked is when does the diode become forward bias and when does it become reverse bias, treating the diode as ideal diode. Okay, all right. So so what are your thoughts about it? We know that N side voltage is plus 12 volt, so the P side voltage has to go above 12 volt, which will happen at this instant of time. So if you look at here, this is the instant of time the diode is going to be forward bias in one cycle. So what is this? This is what we need to find out. So if this period is say t1, the entire cycle is capital T, so fraction means t1 by t, so that is a fraction that we are interested in. The entire cycle is capital T, and out of that some portion it is going to be forward bias because V in is going to go above the N side voltage, which is a constant 12 volt. So what is that point? So it has 2 points here, say like a small t1 and say a small t2. Okay, so we can say V in of t becomes 12 volt. So t1, okay, it becomes 12 volt at what point of time? So the point of time at which it is going to become 12 volt is found out by 24 sine 2 pi by t t1. Okay, so this is, everybody understand what I wrote here? We are saying that the P side voltage has to become 12 volt, then only, or in other words we can say that when V in is greater than 12 volt, that is the time the diode turns on and it become equivalent to a closed circuit or a closed switch. If it is lesser than 12 volt, then because the N side is fixed at 12 volt, so P side has to go above 12 volt so that this VD become positive. That's the only way VD can become positive, right? Only when the input voltage rise above the 12 volt. So the critical point is that 12 volt. So that is why we are equating 12 volt to 24 sine 2 pi by t into t1. Now this is basically an angle. Okay, so let's call it as say theta. Okay, so sine theta is equal to half, right? If I take 24 to the other side, it is 12 by 24, which is half. So what is the value of theta? Can you tell me? Hello, can somebody tell me?
So 60 degree. 30 degree.
Sine what is half?
30 division.
30 degree.
30 degree.
30 degree. So at 30 degree you will have this transition from diode becoming reverse bias to forward bias happen. Okay, so whenever the input voltage is somewhere here, this region from 0 to t1, okay, this is 0 to this small t1, that region it is reverse bias, and then you have forward bias here, and then entire this region it is again reverse bias. So reverse bias, forward bias, reverse bias. Okay, so we are interested in what is the fraction of forward bias with respect to the entire cycle. So we found that total T is corresponding to theta is equal to, theta total is basically 360 degree. So if you can find out, in other words, what is the angle for which it is on, that is this period where it is forward bias. So we found out one point, which is this corresponds to theta 1 equal to 30 degree. Can you tell me what is this point? Then we can subtract from this. Okay, so theta 2, if you can find out, can you tell me what is this point? It is symmetric and the center is 90. So now you can think. So let me call this as theta 1. So theta 1 is 30. That is the time in which diode is turned on. Now can you tell me when is the diode turned off? Which is another solution. So what is going to be that point? It is 90 plus 30, right? Let me see. Yeah, at 30 it is turned on, then it goes to 90. So there is a 60, and then 90 plus 60, right? Are you following me?
Yes, sir. Can you say it again?
Okay. Everybody knows that this peak happens at what angle? This is pi by 2, right? Sine is peaking at theta equal to pi by 2. This is pi by 2 point. So at 30 it turned on, and then this much is 60 degree. And since it is symmetric, there will be a 60 here also. 90 plus 30. Sorry, 90 plus 60. 90 plus 60. So 90 plus 60 is how much? It is 150 degree. Understood? First, when theta becomes 30 degree, okay, the input voltage become greater than 12 volt, and that point from this angle we are finding out the first occasion is when theta 1 that is equal to 30 degree, sin theta 1 is half. We found that. The next occasion is after it crosses 90, it has to go the same amount of angle to the right side. So from 30 to 90 there is 60, then another 60 it has to go where it rises symmetrically with respect to the 90 degree point. It symmetrically decreases, and therefore we can say that it is 150 degree. So total is 360. Now you tell me the fraction. The required fraction is what? Total angle is 360 for one complete cycle, and it is on from 30 to 150, which is 120 by 360 degree, which is what? 1/3. For 1/3 of the complete cycle it is on. If this 12 volt was not there, it will be on for 180, which is half. Fraction will be half. So by putting a voltage source here, we can reduce the conduction